Amphoteric Materials in Chemistry, a short essay by Bruce Mills, otherwise known as the Obligate Pedestrian. The concept of acid has been around for centuries. It has been given multiple definitions. When a concept is like that, it should not be viewed as defined by the most recent definition. Clearly, there is an intuition that people have tried to give precise form to. This results in multiple specific definitions, all inspired by the same intuition. Acid is sour, base is bitter. Sour opposes bitter. Sour plus bitter makes salty. It is said by some that the first theory of acids was proposed by Nicholas Lemery, 1645 to 1715, in his A Course in Chemistry, 1657. Robert Boyle, 1627-1691, seems to accept the principle of acids in his The Skeptical Chemist, 1661, and Chambers' Cyclopedia, 1728, gives clear definitions. The Chambers' Cyclopedia defines acid as anything that affects the tongue with a sense of sharpness and sourness, and says that a confirming test is whether it turns syrup of violets red, but also states that there are dubious acids which turn syrup of violets red but do not taste perceptibly sour. Then defines acid in the broader sense as something that turns syrup of violets red. Acid and alkali is described by Chambers as the grand division of natural bodies, the idea that all things are either acid or alkali, never either, never neither, one or the other, a dichotomy. But in the previous episode it was revealed that John Freind strongly objected even to the basic idea of acids and alkalis. John Freind, 1675 to 1728, in his Oxford Lectures, 1704, demurred. He felt that the idea was a badly defined mess and could not see what the fuss was about. Some of his complaints were ill will, but he also claimed that chemists were inconsistent in deciding which was which. This requires more discussion. Page 13 of the Oxford Lectures on Chemistry, 1704, by Freind. It may be thought, perhaps I ought to say something of acids and alkalis, words which are now in everybody's mouth. But I cannot see what definition can be adequate to them, as they are pretended to be repugnant and contradictory to one another. I ingenuously confess I am so far from comprehending what these terms really signify that I don't thoroughly conceive what the chemists themselves would mean by them." End of quote. The definition given in Chambers' Cyclopedia is essentially that an acid is something that tastes sour and turns syrup of violets red. An alkali is something that tastes bitter and turns syrup of violets green. Also, an alkali in solution mixed with an acid reacts strongly, producing bubbles and salt. Lemons are sour and acid, while burned plants are bitter and alkali. In 21st century terms, the bubbles typically signal the creation of hydrogen, oxygen, or carbon dioxide gas, depending on the details. And at one point, salt was defined as that which is obtained from reacting an acid with a base. Syrup of violets is literally just violets, the flower, steeped in hot water with added sugar. There are acid indicators in violets and in a variety of other flowers. Regarding the opinions of Freind, the course in chemistry first came out in 1657 before Boyle's Skeptical Chemist, 1661. I am working mostly from the third edition, 1698, of A Course in Chemistry. It appears to have been considered still fairly current in 1713, when the 10th French edition came out. In 1762, the edition augmented by M. Baron came out, with a particular note that had been updated with material unknown to the original author, so that Lemery, then Boyle, then Baron's modification of Lemery. Freind came in the middle of this, 1704. He had a point in stating that the colour change is not quite as simple as that. Putting lemon juice into syrup of violets turns it light purple or pink rather than red. Strong vinegar will turn it a rather cherry red, but this is a matter of pragmatic details. It is a quibble, not a fundamental problem. Robert Boyle wrote in Ariel Noctiluca, 1680, Section 1, on artificial phosphori, Observation 7, acid and alkaline spirits being reckoned the most subtle and operative substances obtainable from mixed bodies by distillation, I thought it worth while to try by the taste whether our shining liquor abounded with particles of either of those kinds. I did not, however, find that the liquor I put on my tongue was in the least acid, nor that it was sensibly alkaline, as the salts and spirits afforded by hartshorn, blood, etc. But it seemed to have an odd empyreumatic taste, almost like the spirit of crude tartar, its smell resembling that of some empyreumatic oil, with a scent somewhat like stale urine. I likewise, for further trial, put a little of our liquor to some drops of blue syrup of violets, but the mixture was not thereby turned green, which it would have been by a quarter so much spirit of hartshorn of blood, or of some other spirit abounding with salt in a urinous nature." End of quote. Empyreumatic oils are oils obtained from organic matter by distilling at high temperatures. Empyremia is a Greek word meaning a live coal covered in ashes. Page 48 of the Sceptical Chimus, 1661. Common tartar, without the addition of anything that is not perfectly a mineral, except saltpetre, may, by one distillation in an earthen retort, be made to afford good store of real salt, readily dissoluble in water, which I found to be neither acid nor of the smell of tartar, and to be almost as volatile as spirit of wine itself, and to be indeed of so differing a nature from all that is wont to be separated by fire from tartar, and divers learned men, with whom I discoursed of it, could hardly be brought to believe that so fugitive a salt could be afforded by tartar. End of quote. The above quote is part of a lengthy monologue on problems in separating salts, the properties of vitriol, acids, and tartar. Boyle is seeing at least some problems with acids and alkalis, and noting that there is a salt that behaves not as an acid salt, where in some earlier texts and in Chambers I see the principle that salt is always acid, although Boyle acknowledges alkali salts. In 21st century terms, there are recognised acid and alkali salts equally. The more general term for the opposite of acid is often base. An alkali is a base dissolved in water. This is getting a theory of acids and bases and salts, where acid plus base gives salt. There follows a list of definitions of these terms, but always staying with this theme. There are several broad themes in chemistry, chemistry, alchemy, and chem that remain through the centuries and the changes of name. One of these is fire, as it seems to be very good at transforming things. In the 21st century terms, it provides the energy, such as the activation energy, for a reaction, but that is just a way of saying that it transforms wood into ash or solid into liquid. The theory of combustion, the theory of metallurgy, the theory of medical materials, the theory of salts, which expanded into a theory of acids, bases, and salts. These are all old themes in one sense or another. Sugars and alcohol are also often considered, as was urine, blood, and saliva. Acid plus base gives salt. However, in the 21st century chemistry, there is acknowledged to exist amphoteric compounds that can act both as an acid or a base. In alchemical terms, primarily, an acid is something that tastes sour, and an alkali is something that tastes bitter, and creates bubbles when put in an acid. So sour plus bitter equals salty. Acid, base, and salt all stem originally from the reaction of the human sense of taste. This gives a classification into sweet, salty, sour, bitter, and savoury. The last is also known as umami. We also react to the sensation of alcohol and chili, as well as hot and cold. Our sense of smell is mainly based on variations and compounds of benzene. While it has not been emphasised in this essay, smell was used, as well as taste, to group materials. Boyle spoke of stale urine smell as an indicator of the progress of the reaction. Umami, at least in European scientific understanding, does not seem to have been recognised until the late 20th century and is now a standard part of the theory of taste. The taste was recognised informally by the Romans and in 19th century Europe. The issue of recognition was whether it was a basic taste for which taste buds exist, and especially the creation of a chemical theory of taste. The word umami is from the theory of taste proposed by the Japanese professor Kikani Ikeda in 1908 at Tokyo Imperial University and accepted into international scientific literature at the first Umami International Symposium in Hawaii in 1985. All of the above gives no reason so far to rule out substances that create bubbles when put in a solution of something that creates bubbles when put in a solution with acid. The important point is an acid does not generate bubbles with another acid, and an acid generates bubbles with an alkali. There is a critical divide that has to be crossed. The first explicit suggestion of an acid-base reaction is said to have come from Guillaume François Roual, 1703 to 1770, who introduced the concept in 1754. This is only a few years before Lemery and his acid theory. A base is a substance which reacts with acid to form salt. In some sense, this is the definition of salt as well. This is part of the shift during the 17th and 18th centuries away from human taste and smell as the primary definition of materials towards visual checks such as indicator colour. Acid was defined as sour and became that which makes syrup of violets red. Alkali was that which tastes like the plant samphire, or alkali or bitter, and became that which turns spirit of violets green. Salt was that which tastes salty and became that created by an acid-base reaction. Later, acid became a proton donor and salt became an ionic solid. The definitions and hence the meanings of the terms change over the centuries, requiring caution in interpreting earlier works. The etymology of alkali has some murkiness, which is common. In the Chambers Cyclopedia 1728, Volume 1, page 62, ALK, alkali in chemistry, a name originally given by the Arabians to a salt extracted from the ashes of a plant called by them kali and by us glasswort, because it is used in making glass. End of quote. In several modern sources, it is stated that alkali comes from kali, spelled with a Q rather than a K, and meaning to burn, and alkali, that which has been roasted or burned, in Arabic. Some sources say it originally meant specifically the calcined ashes of the glasswort, and then later of any plant, and then alkaline in the more general sense. Some sources say it originally just meant ashes, and then specifically the ashes of the glasswort, as in making soap. However, in that case, it seems that there is as much evidence that the plant named the ashes as the ashes named the plant, and it could have been something of a linguistic coincidence in the same sense that the origin of the root chem for alchemy and chemistry might mean black, Egypt, or metallurgy, or perhaps all three without there being one true source of the name. Humans have always loved wordplay and a good pun. In conclusion on this etymology, I suspect that the two theories are really essentially the same theory with nuances that are impractical to distinguish. In 21st century chemistry, a salt is a chemical compound that is an ionic assembly of smaller units with no net charge. However, in the 17th and 18th century, such a definition was not available. There seems to have been a sense of the word salt that meant the calcined ashes of organic material, as well as the nuance of the important heart of the material. Calcined means burned to ashes and pulverized. It is true that salts and minerals are likely to be what is left, nothing organic. This usage continues into the 1800s. In particular, Abridged Therapeutics, founded on histology and cellular pathology by Schussler, 1880, speaks of salts as that which is left after calcination of animal tissue. Some of you might react to the use of Dr. Schussler due to his association with 20th century homeopathy. However, those who are negative about the reference, please keep in mind that I'm not supporting homeopathy. Schussler's book is a worthy study of the importance of non-organic substances in living tissue. And for those who are positive about the reference, keep in mind that I'm not supporting homeopathy, but using Schussler as an example of a well-trained medical person and his attitude to the word salt in the 19th century. I'm also not attacking homeopathy, just reporting on the history. Later, salt became that which is produced from an acid-base reaction. Since in some texts it is seen as the important material left from calcining, this would resonate with the phrase, the salt of the earth. Some sources suggest that salt is used here in terms of the value of the salt, which was hard to obtain, the valuable part of the earth. But this is not very distinct from being the essence left over after the material has been burned. Neither do acids and bases have just one singular definition. The definition splits into at least three basic ideas. There are Arrhenius bases, Bronsted bases, and Lewis bases. In 21st century terms, or rather in 19th century chemistry, hydrogen is the lightest element, hydroxide is the oxidized hydrogen, HO-, water, H2O, and hydronium, H3O. Hydrogen hydroxide is just water, hydronium is the actual acid component in water, free hydrogen ions attached to water molecules. Arrhenius bases, something that provides hydroxide ions in water. Arrhenius acid, something that provides hydrogen ions in water. The hydroxide being negative was attached to something positive. The hydrogen being positive was attached to something negative. The reaction combines the hydroxide and hydrogen to form water, and what is left is a combination of positive and negative species, a salt by definition. The reaction between Arrhenius base and Arrhenius acid produces a salt plus water. The water might go unnoticed in an aqueous solution. In a sense, then, water is both an Arrhenius base, in that H2O can provide an HO- ion, and an Arrhenius acid, in that H2O can provide an H plus ion. H2O splits into H plus HO-. Another idea of acid is the pH of the solution. This essentially comes from a balance. Water is neutral when the hydrogen ion and hydroxide ion balance each other out. This occurs at a concentration of one particle in about 10 million, and pH is negative log base 10 of this concentration, hence neutral is often defined to be when pH is 7. The idea, however, is a bit off the mark. The dissociation of H2O into H plus and HO- depends on the temperature. At 50 Celsius, neutral is 6.63, not 7. It should also be pointed out that pH does not have to be positive. It is literally negative log base 10 of the hydrogen ion concentration. It could be less than 0, or for that matter more than 14. An alkali is usually defined as a base that is soluble in water. A Bronsted acid donates a proton, which is a hydrogen ion. A Bronsted base accepts a proton, as for HO- accepting H plus and becoming H2O. However, HSO4- can accept and donate H plus, and hence is both acid and base, or as some would have it, can act as an acid in one reaction and a base in another. So it is not so much that it is an acid or a base as it takes on that role. Finally, a Lewis acid is something that can accept a pair of non-bonding electrons, and a Lewis base is something that can donate a pair of non-bonding electrons. It is crucial to realize that this definition is given specifically within the sophisticated theory of quantum chemistry and is not a direct experimental definition at all. It is common for people to gain a delusion that quantum chemistry is very practical in its definitions because it is often accompanied by a very geometric intuition. However, things such as orbitals and the number of non-ionic bonds are based soundly on the abstract theory and only very indirectly on practical measurement. The Lewis acid concept vastly generalizes the concept of an acid-base reaction beyond the chemical and other chemical definitions. It forms a kind of generic complement to the generalized concept of oxidation. Oxidation in quantum chemistry is the transfer of an electron from one atom to another, with a change in the oxidation number of one or more atoms. The oxidation number is the charge on an atom if it is assumed that all its bonds are fully ionic, involving a complete transfer of an electron. Many reactions involve two atoms with outer shell holes and electrons. A transfer is oxidation reduction, and a sharing is Lewis acid base. It is not my intention here to confuse or to suggest the situation is so confusing as to be untenable, nor even to teach quantum chemistry, merely to state that from about 1650 to 1950 there are a lot of changes in what exactly it was supposed that an acid and base were, and to give a naive view of what they were. None of the people involved were wrong or right in terms of the definition of acid and base in a salt. There is no universal objective definition of language. Rather, each person in their own time was trying to come to their own terms with an apparent consistency in the way that matter reacted with other matter, and the eventual definition, which may well be stable, turned out to include several distinct cases. This is a common progress and outcome in science. The core idea is acids taste sour, bases taste bitter, an acid and a base react together to form a salt. The situation is complicated by the fact that this often occurs in water, so salt might precipitate or it might have to be extracted by dehydrating the solution. Lemery's early theory of acid and base is that acid is a particle with spikes and base is a particle with holes into which the spikes fit. This on the whole does not seem to provide much in the way of explanation. Freind developed a theory in which the particles attract each other to a differing degree depending on distance and orientation. This is closer to the 21st century view, but it was not really workable. Lavoisier said that an acid was something that provided oxygen, and the term oxygen means acid generator. At the same time, Cavendish suggested that an acid provided phlogiston, but by that time, at the end of the 18th century, phlogiston was identified as what Lavoisier called hydrogen, rather than the earlier concept of negative oxygen, or even the earlier concept of the element of fire. In the early 18th century, Humphrey Davy demonstrated that some acids did not have oxygen, and so Lavoisier must be wrong, but he did not provide another theory. Jöns Jacob Berzelius suggested that acids are oxides of non-metals and bases are oxides of metals. In 1838, Liebig suggested that an acid contains hydrogen, but that will react to give up the hydrogen for a metal. This fairly much completes the shift from oxygen-based acid theory to hydrogen-based acid theory. Arrhenius in the late 1800s suggested essentially that an acid donates a hydrogen ion and a base accepts it. In this sense, the acid component of water is not hydrogen, but hydronium, which is an ion formed by adding a gratuitous proton to a water molecule, keeping in mind that a hydrogen positive ion is just a single bare proton. The behaviour of water is surprisingly complicated and unique. In some ways, this finally gives a vague justification for the focus on and the importance of acids and bases. The key idea is that there is a bare proton, a subatomic particle, moving about from place to place. A positive hydrogen ion is a bare proton. This makes it different from any other element ion, and in many senses a kind of positive complement, or better rather massive one, to the negative electron. This gives a basic idea of what was thought about acids and bases and salts from 1650 to 1950 or so. It is background from which we can consider more details of the specific issues such as tartar.